exam. I think I had told you that I said that most of the time exam 3 is a pretty strong exam, and the results I think speak for themselves. I erased all the data that I had up there. Great, good job. The average was about an 80. Standard deviation was 19. We had, let's count them. Highest grade in the class was a 110. That's the highest score you could have possibly got. That's perfect test with the bonus. And we had a couple of, let's see, these are all A's, A's up to there, and then we got a couple of B's, a couple of C's, a couple of D's, a couple of F's. All right, so overall, I think it was good. I'm not concerned about the test. So I'll hand those back to you at the end of class. Feel free to look over those, and if you have any questions, I'll be happy to entertain questions, all right? But try and figure out what mistakes you made once I give that back to you. Any questions or comments or concerns about the test right now? Okay, because I think we need to move on. Okay, so last time, which I'm sure it seems like forever ago for you, we were in 8.2, and in 8.2 we were talking about 3 different types of common series. And so the common series that we had started discussing were geometric, harmonic, and we had not talked about this idea of telescopic, or you could also call these collapsing series. So those are the 3 types of series that we are investigating in this section. Does that sound familiar? And everyone has their little cheat sheet that I gave them that has all the different ways that we approach series, right? Okay. So if you look off that cheat sheet, we have the Nth Term Test, which was the first thing you always want to do when you see a series. Take the limit of the sequence part, see if it goes to 0. If it goes to 0, you don't know anything. If it goes to something other than 0, you can say it diverges. Then we have geometric series, and that's what we talked about here. And we said that that series, you can find the sum of that series if the condition was that the absolute value of r had to be less than 1. And in that case, it converges to a over 1 minus r. So this is all on this sheet, and you can look back in your notes. We did that. And then do you remember at all what I talked about, what I said about harmonic series? They what? They always diverge. So a harmonic series looks like this. It's a constant over n. Any constant over n, anytime you have a series like this, this will diverge. And I tried to convince you by showing you this sum, and oh, this will add up, and this is bigger than a half, and that's bigger than a half, and that's bigger than a half, so it blows up. So I hope that we can just put this away and say harmonic series diverge. Is that all right with you? Okay, so we're going to talk about telescopic now. So before I do telescopic, I want to remind you of one thing, and that's this. When we say that we have an infinite series, right? When we're looking at an infinite series, we say that this will converge. Remember, the arrow means converge, that converges to some s, some sum s, right? What this means is that if we take the limit as n goes to infinity of s sub n, we get s. Do you remember what s sub n is? The nth partial sum. This is us taking all these little guys and creating a new sequence from it.
Like the sequence of the sequence.
It's the sequence of the sequence, exactly. But that new sequence was the sum of the pieces, right? So this right here, I'm going to need this right now, just to remind you that that's what it means. For us to say a series converges to S, means that we have to show that the limit as n goes to infinity of the nth partial sum goes to S, or equals S. Another way we could write this is to replace this with what it is, which is the sum k equals 1 to n of a sub n. So this right here means that we're going to add up not the infinite number of these terms, but the finite number of them, stopping at n. So this is that. Okay, just don't forget that because I'm about to use that. All right, let's look at a telescopic series then. What example am I going to do here? Yeah, let's do that one. So let's take a look at the series sum n equals 2 to infinity of 1 over n squared minus 1. So let's start running through what we know now. Let's first do the nth term test. Nth term test says we need to look at the sequence. The sequence is this piece, right? Take the limit as n goes to infinity of the sequence 1 over n squared minus 1. And what does that limit go to? 0, right? Fixed number over something that gets big, that goes to 0. So since that goes to 0, what does the nth term test tell us? Nothing, right? Okay, so the nth term test fails. All right, next thing. Is it a geometric series? Why not? Okay, so the thing that lets you know whether or not you're looking at a geometric series, remember this is what a geometric series looks like, right? The key is that the n, right? This thing, the index, the n, is up in a power. That's what geometric series look like. You have some number to a power. Here we have the index n is down in the base. It's not an exponent. So this is automatically not geometric. Agree? Okay. Now, is it harmonic? So harmonic, I said, looks like c over n. And the big thing to see here is that when I say n, I mean n to the first power. So this right here is linear. Linear in n. It's linear in n. So harmonic series have to be linear in n. That's quadratic in n. So it's not, it's of the things we've looked at, it's neither one, right? And it's also failing this test. So what is it? Well, let's start writing out this series. Okay, let's just start plugging some values in. Okay, so let's plug things in. Start out with n is 2, right? Do you see why I'm starting at 2 and not 1? Because if I start at 1, it's going to be undefined. So I started at 2. So plug in 2 first, you get 1 over what? 3? Right, 2 squared minus 1, so 3. And then you say plus. What's the next one? So now you plug in 3, right? 8. Plus, next one, you plug in 4. So 1/15. Plus, dot, 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 and that keeps going, right? So I look at that and I'm just like, well, okay, I don't know. Does this add up to be something? Does it converge? I have no idea, right? No idea. So what can we do? What can we do? Well, we have to realize that this is a telescopic or a collapsing series. And to see that requires us to go back into our database, I guess, in our brain and realize that this is the same as this, and that can be written like this. So what am I bringing into play here? Partial fractions. Right? Now we did partial fractions when we did integration, didn't we? But I'm actually going to do partial fractions on this, and let's just see what happens, okay? What we're saying is there a way to rewrite this so that it looks like something else? Well, yeah, we can factor the denominator. Since these are distinct linear factors, I can rewrite it so it's going to be the sum between two pieces. So we now need to go figure out what A and B are. So we did this before, right? I'll just kind of cut through all the little ancillary work, but you clear fractions out, right? You get something like that. And then how could we figure out what A is? We could use a little shortcut method here. To figure out what A is, we could let n be what? -1. So if n is -1, what does that equation become? -1 minus 1. So I'm replacing all my n's with -1. -1, that's going to kill this off, but that's going to become a -2 right here, right? So what's A? -1/2. Can I trust that you could get that? Or is everyone following? We've done this before, so. All right, now how would I get b? Let n be 1 this time, right? And that will kill this off. So if n is 1, we get 1 equals, we know that that's dead. Replace that with 1. So when you solve for b here, you should get b as positive 1/2, right? Okay. So we go back and we say, all right, let's look at this series again. We're going to take another look at it. Because right here, it was just something plus something plus something plus something forever, right? But if I rewrite the series in an equivalent form, right? This is the same expression. I haven't written it. Oops. This should be the same as a negative 1/2 over, what was the first factor? N plus 1. And then plus b, which is 1/2 over n minus 1, right? That should be the same series. Because all I've done is algebraically transformed that inner piece. So that should give me the same thing. I should say it this way. That should add up to be the same thing, right? Now, as I start writing out the pieces, it's going to look different, but the sum should be the same. The infinite sum should be the same. Now, do you see that both the numerators have a 1/2 in them? Yes? I'm going to factor a 1/2 out of both of these. And then I'm going to bring the 1/2 out of the sum. So constants can come out of sums just like they can come out of integrals. So this becomes 1/2 sum n equals 2 to infinity of, I pulled out a 1/2, right? So negative 1 over n plus 1, and then plus 1 over n minus 1. Y'all comfortable with that? See what I'm doing here?
So,
Yes? Oh, that was given. I gave it to us that way. Yep, I gave it to us that way. Okay, so now let's start writing this out. Wouldn't this be 1/2, right, times whatever this sum is? Right, so 1/2 times whatever that sum is. Now let's start plugging things in here. Let's start with n equals 2 and see what that first piece would be. So what would happen if I plug in 2 for n? I get negative 1 over 3, then plus 1 over 2 minus 1, right? So 1 over 1. With me? Plus, now what would the next one be? So now I'm plugging in 3 for n, right? So negative 1 over 4, and then plus 1 over, I'm plugging in 3, 2. Still good? Okay, let's do another one. Negative 1 over 5 plus, plugging in 4 now, right? 1 over 3, hold on. 1 over 3, I thought I saw 1/3 somewhere. Oh, there was a negative 1/3 out here, wasn't there? Negative 1/3, positive 1/3? Wouldn't those cancel out? Let's do another one. Where am I at? Plugging in 5 now, so this would be negative 1/6 plus 1. Wait a minute, I thought I saw, I did see, look, that one's gone, right? You see this? Do you see that I'm starting to create pieces that are going to cancel with things over here? And now this goes on forever, doesn't it? I'm going to close it out. So the key to telescopic and collapsing series is this. You first have to convert it into something that's going to have 2 terms in it so that you can start to get canceling. So notice one of these was negative, the other was positive. That's what happens when you do your partial fractions. So instead of, like in the very beginning, we just had something plus something plus something plus something, right? But now we're getting like something plus something, something plus something, but some of them are the same thing, so they're going to cancel, right? They're off by a sign. So we have to now establish what the pattern of cancellation is. So let's see if you can follow this logic. Let's say that I call this, right here, what's in this parentheses. Let's say I call this my first guy, all right? And it's 2018, so I got to be really careful about inclusion here. So is anyone offended or anything? Can I continue with my second guy, third guy? Everyone's good? Okay. Second guy. This is my third guy, right? And so on and so forth, right? Now, in the first guy here, I've got two terms, right? I have a first term and a second term. First term, second term. First term, second term. So what's the pattern? I have the first term, right? The first term in the first guy gets killed by who? The second term in the third guy, right? That's what's happening? The first term in the first guy is getting killed off by the second term in the third guy. So let's move to the second guy. Look at its first term. Who does this first term here gets killed off by who? The second term in the fourth guy, right? Okay, so, and then what about this negative 1/5? It's a first guy, or it's a first term, right? The first term here, would it get killed off? By who? The second one down here within my dot, dot, dot. Okay? So if I'm trying to summarize this to someone, I would say this. First terms killed by second terms. My first terms are always killed by second terms, right? But those second terms are two guys down, right? Always. Two guys down. Does that make any sense to you? I'm trying to explain this to you the way that I see it. You're not going to read this in a textbook like guys in terms. Does it make sense to you? Okay. Now it's important for us to establish this pattern right here. That first guys are always killed off by second guys 2 terms down. Because I know this is gone, right? This is gone. I know this one's gone, and that one's gone. I know that one's gone with one from over here. Now what about this negative 1/6? Would it be gone? It would be gone, right? Because it's going to be killed off by a second guy 2 terms down, which isn't here, but it's there. I mean, it's down there, right? So that guy's gone. So what's still left over here? 1. Is this one killed off? Why not? Is it a first guy or a second guy? It's a second, it's a second term, I should say. It's a second term, right? Second terms are killed off by first terms, but 2 upstream, not downstream, right? Yeah, so since this is the starting one, there is no guy 2 in front to kill this one off. So this one stays, doesn't it? And then this one stays, right? And this one did get killed off because there was a first term 2 upstream. That kind of makes sense? Okay, so I've established the pattern. Now I actually have to go through and do the final computation. So here's how we're going to do this. And on a test, this is what most students get points taken off on, is that they try and just give me the answer from this. You can't do it that way. What you have to do is this. We have to establish what S of n is. Okay, so all of that work up there was just to get me to this next step. I'm going to write down what we're going to call the nth partial sum, which we've talked about this. This means we're going to add up the first n, right? Okay, so when we do this, it's going to look like this. It'll be this first one, right? And there's let's do the half in front. Let's put the half out here in front. 1/2 bracket. Okay, so then It's this first one, which we've already done. I'm writing very small on purpose. Then I have my second one. Then I have my third one. And I'll go one more. Plus dot, 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 right? But I'm going to stop this time. And I'm going to stop when I get to the nth one, to the very last one in my partial sum. So the nth one, way down here, would be what I get when I plug n in to this. So what happens if I replace n with n? You just get that, right? So my very last one down here is negative 1/2. Oh no, we pulled a half out, sorry. I meant to say here. So it'd be negative 1 over n plus 1 plus 1 over n minus 1. Y'all agree with that? Okay, now what's the one right before this one? So I'm not going to be plugging in n, I'm plugging in what instead of n? 1 less than n, right? So n minus 1. So what would happen if you plug n minus 1 in right here and n minus 1 in right here? What would you get? Negative 1 over n, right? So that's 1 less than that. And then what's 1 less than this? 1 over n minus what? 2, right? So that number there is 1 less than that number, and that number there is 1 less than that number. Now, when should I stop going backwards? Probably one more time, because I want to be able to see the cancellation happen. I want to be able to see that first term kill off the second term 2 guys down. So I need at least 3 of these to see the pattern. So I need to go back one more. This will be negative 1 over what? N minus 1, and then plus 1 over n minus 3, right? And if you wanted to, shoot, you could squeeze another one in here if you wanted to. Plus, let me just go ahead and do that. I'll try and force one more in here. So you probably realize now you should have been writing sideways on your paper. N minus 2 here and 1 over n minus 4. All right. You ready to do this? We're going to start canceling a bunch of stuff. Oh, and I need to close my bracket here. Any questions on this? On what I have written down here? Where I came up with it? Okay. This 1/3, right? And that 1/3 are gone. I'm going to connect them so we can see the cancellation. This 1 doesn't leave, right? Stays there. This negative 1/4, does it go away? Yes. Down here with that one. Gone, gone. How about this 1/2? We already said it's a second term, right? It needs a first term 2 down. It's not there, so that stays. Okay, how about the negative 1/5? Does it go away? Yes, it goes and it cancels with something inside that dot, 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 right? So that one's gone. How about my negative 1/6? Does it get killed off? Yes. By something down here in that dot, dot, dot. Now let's go over here to the back end of this finite partial sum. Let's start with this one. This is a second term, right? Second terms are killed off by first terms 2 upstream. So if I look 2 up at the first term, this is going to match this. Does it? Right there, right? Those match. One of them's negative, one of them's positive. Gone. Now this one is a first term. First terms cancel with second terms 2 down, right? That term doesn't have anything to kill it off because I've stopped, right? So this guy stays. Do you see that? Hello? Yes? You see it? Okay. What about this one? This is a second guy, or second term, right? It gets killed off by first terms 2 down. It's there. I actually put one there so I can see it. There, and that one, gone. This is a first term. First term gets killed off by second term's 2 down to the right. I don't have a 2 down to the right, do I? So this one stays. I'm boxing everything that's not going away. And then what about this one? This is a second term, gets killed off by first terms that are 2 upstream, right? And is it up there? Somewhere, right? It's in the dot, dot, dot now. So this one right here gets killed off by something in that dot, dot, dot. This one already went away. This is a second term. It gets killed off by first terms 2 upstream. Somewhere in that dot, 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 this one gets killed off. Now, that means that my partial sum, S sub n, can be rewritten as 1/2, and then what's still here? 1 plus 1/2 plus, all this is gone, isn't it? Everything in here is gone. Everything on the inside has collapsed, right? Like a bridge. You got the one end of the bridge, the other end of the bridge, you got the bridge, the whole bridge is collapsed. All you have are the 2 posts at the end holding it up, right? That's why they call it a collapsing series. They also call it a telescopic series because you know those old school telescopes that are just like handheld? You kind of pull them out and you look, and then when you're done, you close them up. The 2 ends come together. That's basically what's happening here. So this end right here, what's left here? -1 over n and plus -1 over n plus 1. That is what the nth partial sum is. So if I go and I add these things up, but I stop at n, here's what I get. So how am I going to figure out the sum of this series? What do we say? If this series converges to S, that means that the limit of S sub n is S, right? We have to take the limit of this now. What is the limit of this as n goes to infinity? That's the final step. What is the limit as n goes to infinity of S sub n? Well, that will be equal to the limit as n goes to infinity of 1/2 times 1 plus 1/2 plus -1 over n plus -1 over n plus 1. And fortunately for us, that's a very easy limit to compute, isn't it? Because that goes to 0 and that goes to 0, which means all you're left with is 1/2 times 3/2. 1/2 times these two together is 3/2. So you get 3/4. It's a lot of work to show that a telescopic series converges, right? Partial fractions establish a pattern, right? Establish the pattern, then after you establish the pattern, write out the nth partial sum, and then after you do that, take the limit, and then there's your answer. Now, do you see up here that we could have got the same answer without doing the partial sum? Do you see that we still would have got that? I've erased it, but we had 1 plus 1/2, didn't we? And at the end of the day, isn't that what we had? Okay, don't do that on a test. Because it is possible that your expressions out here are not -1 over n. This could turn out to be n. And if that's n, then that goes to infinity, and that diverges. So you cannot just say, oh, here's my canceling, and then assume that the tail end is going to go to 0. You can't. You have to see it in the partial sum. So that's kind of danger zone. What do y'all think? It's kind of weird, huh? But we actually found out what it added up to be, didn't we? 3/4. So I'm going to bring in my computer here to see if we got the right answer. I'm going to actually have it plot the sequence, and then it's going to plot the series, and we're going to see if 3/4 looks like a reasonable answer. So I've put in the series here. The series was 1 over n squared. Oh crap, I'm going to have an infinity here. I'm going to have an infinity because, what was it? N squared minus 1, right? I have to trick my computer because my computer is going to start at n equals 1. So I'm going to trick my computer by putting plus 1 in here and then minus 1. Okay. So we did this before in class, right? So I showed you, like, here's the sequence. It gets smaller, it approaches 0, which tells us nothing. But as we start to do more and more points, we can see the sum. Look at it over here. 0.72, 0.73, 0.74. I've only gone out 100 terms. Let me go out 800 terms. 0.747, it's starting to slow down. Okay, I think I'll stop there. Maybe I can just jump to it. Yeah, I can just jump to it. The dragging causes problems. We got 1,200 terms. It's thinking. Okay, there we go. 0.749. So if we keep going, this is going to get closer and closer and closer and closer, and it's going to converge to 3/4, 0.75. All right? So when it comes to series, we can find the actual sum of geometric and telescopic. Telescopic and collapsing are the same, okay? I'm writing this note down for you because I think this is important. If on your test, which there's only one test left, right? If on a test or if on a quiz, I tell you, find the sum. That is a hint that you're looking at either a geometric or a telescopic series. Because otherwise, we can't find the sums. We can tell you it converges, we can tell you it diverges, but we can't tell you what it converges to, all right? So if it converges and it's geometric, then we can find the sum. If it's telescopic and it converges, we can actually find the sum. Otherwise, it's just a thumbs up or down for convergence. Understand? All right. Let's take a look at another type of telescopic. I don't think I'm going to work through this, but I want you to see another version of a telescopic. Sum n equals, let's start at 3 to infinity of natural log of n over n plus 2. Now, this is telescopic, but let's act like we didn't know that, okay? So the first thing I would do is the nth term test. I would do the nth term. So I do the nth term by taking the limit of the sequence, right? So take the limit as n goes to infinity of natural log of n over n plus 2. And what is that equal to, and why? ln of 1. Okay, so what's happening is the limit of the natural log, you can move the limit inside, you get infinity over infinity. So you could use L'Hopital's rule. If you switch it over to a function of x and all that, you get derivative of the top, which would be 1, derivative of the bottom, which would also be 1. So you get 1 on the inside. And what is natural log of 1? 0. So that limit goes to 0, which tells us nothing. So this fails. Now just think about this. What if this problem would have been 2n right there? then that would go to 2, right? And natural log of 2 is not 0. And then you would have said, right now, you would have said diverges. Okay? But it wasn't 2. Just want you to see how much time you could save yourself if you run the nth term test quickly. Make sure you're almost saying, I got to have 0 here in order for me to start looking at other things, right? Otherwise, it diverges. So that didn't tell us anything. So now we ask ourselves, is this geometric? Well, n's not up in a power, right? Okay, is it harmonic? Do you have a constant over linear? No, you've got natural log. What the hell? It's not even close to harmonic, right? So the only other thing on the plate right now is telescopic. So let's say we start writing things out. Plug in, I'm starting at 3 here. So what happens? It would be natural log of 3/5, right? Plus natural log of, plug in 4, 4/6. We could reduce that, but natural log of 5/7. Am I doing that right? Yes, right? Plus dot, dot, dot. We're trying to figure out what that converges to, if it even converges. I'm telling you this is telescopic. And it doesn't look like the last one we did, right? I can't do partial fractions on this. But the whole idea behind partial fractions is that we took the expression, we were able to make it into 2 pieces where they started killing one another off, right? We had like one of them was positive, one of them was negative. Is there anything that you can do that's going to do something similar to that here? What? Huh? What? Huh? Property of logs. What's the property of logs? I think you mean this. If you have the natural log of, if there's division, that's a b, then this is natural log of a minus natural log of b. That's a property of logs. Subtraction between 2 logs turns into division within 1 log. So this could be rewritten as sum n equals 3 to infinity of natural log of n minus natural log of n plus 2, right? And then as you start plugging in your values of n, you're going to get 2 pieces each time, aren't you? What would happen if I start out with n is 3? My first piece would be my first girl. I better not go there. I better not go there. Natural log of 3 minus natural log of 5, right? And then the next one would be plus. Now we do natural log of 4 minus natural log of 6, and then plus natural log of 5 minus natural log of 7, and so on and so forth, right? And do you see the cancel? Do you see where it's going to happen? Second terms and first terms are going away again. They're killing each other off. And it's actually 2 down again. But it doesn't always have to be 2 down. Sometimes it's 3 down. Sometimes it's 4 down.
Is it always going to be the second term?
It should always be a first and a second. It doesn't always have to be the second here and the first here. It could be the first here and the second there. But it should be, one of them's the first term, the other one's the second term. Those are the ones that kill each other off. Okay, so I'm going to stop this problem, but let's talk about what you would do next. Once you establish your pattern, what do you do next? Go to S sub n, right? And you write it out. You write out the first couple of pieces plus dot, dot, dot. You write out the last few pieces. Start showing your canceling. And then once everything collapses out, you'll have some stuff from the front, some stuff from the back, and you take a limit. Now let's just think about this one for a second. I think this one's going to possibly, I don't know. I think you might, I don't know. I want you, you can do this one. There's one like this in the homework, so I'm curious to see what happens at the end. Because we know that we're going to have some natural logs at the end, right, that stay. And when you take the limit as n goes to infinity of a natural log, doesn't that become infinite? Like natural log of infinity, isn't that infinite? But you're going to have more than one of them. You're going to have 2 of them. So you're going to get like infinity minus infinity, which is indeterminate. So you're going to have to do something with that. Maybe put them back together using the property. You'll see. Do your homework and you'll see what I'm talking about. I don't want to be a total spoiler here. Yeah. Okay, we're done with 8.2. Make sure you do your homework. And I was thinking about this because, this happens a lot. We get to this point, like Thanksgiving is right around the corner. There's basically only one more exam left. Some of you have set yourselves up very well with your grade where, you're in a position where, you could come in and you could get a 40 on the final and still pass the class, and that's good for you. I'm happy if that's the position you're in. But I think that this Chapter 8 material is some of the most important material. I wish we could start with Chapter 8. I really do, because it's that important to me. I think that if you're going to see anything later, I mean, of course you'll see integration and other aspects of what we've talked about, but the series is probably the most useful thing that you will see later. So I guess what I'm getting at is don't be like dragging yourself to the finish line, I could have got an A in the class, but I'm burnt out and I'm just going to stop paying attention. Who cares? Because this is really the place where if you can't understand this, you're going to struggle. No matter what, like moving on in math, you're going to struggle. If you have trouble with this, you're going to have trouble later. So give every effort you can to try and understand what's going on here. All right, 8.2. 8.3, sorry, 8.3. Boy, we still have a lot of stuff to talk about, huh? (8.3). The integral and comparison tests. So we want to start off first with a theorem for this one. So a theorem is a mathematical statement that's true, all right? And it's been proven. If you have two series, now this means, remember this means like n equals 1 to infinity, n equals 1 to infinity, but I'm not writing it, so it's understood. So let's say we have two infinite series. If these series both converge, then so do this one. So what is this telling me I'm allowed to do? If I have two series that converge, I can put them together into a new series with addition or subtraction, and that series will also converge. All right?
Could you use that the other way, like if you were to get a series and you're adding two aspects, could you separate it into test?
I'm glad you asked me that question. I will answer your question after I finish writing the different conditions, okay? So that's true. And then, so does any multiple of the series. So what this theorem is basically telling you is that if you start with two convergent series, that adding or subtracting the two convergent series together, you maintain convergence. And if you multiply the series by any number, you still maintain convergence. Now, the question that was just posed, very good question. You see this problem that we did a second ago? I think it was 3 or 2. Maybe it was 2. This one, 1 over n squared minus 1. Did that converge to what? 3/4? But when we rewrote this, didn't we break it up to be, like there was a 1/2 out there, right? But it was like negative 1 over n plus 1 over n minus 1, wasn't it that? Oh, this one was plus 1? Okay. And that one was n minus 1. Yeah, duh. Okay, so that's what we had, right? So look at this. Look at this real quick. Is that right there by itself a convergent series? Yes or no? Not with this, just that. If I gave you that, if I said, hey, everyone, does that converge or not? You think yes? What does this look like to you? Harmonic, doesn't it? And all harmonics diverge, don't they? So that by itself is divergent. That by itself is divergent. But the two together is convergent. And it's because, look, this is going to like negative infinity because it's negative. This one's going to positive infinity. So you have this idea of like indeterminate form. Together they come together. So this theorem is saying that, look, you're allowed to take series and split them up and do them separately. So you can do them like this. I should put this in here. I forgot to put this in here. Okay, so this is the property that we're talking about here. If these are convergent, then you can add them together, it'll still be convergent, or you can split them apart, it'll still be, each one will be convergent. So you're allowed to split apart, as long as they're both convergent to start with. See here, we can't split this into two different series and do them separately. I can't do like this one and then this one apart because they're divergent by themselves. So I'm not allowed to split them. Does that make sense? You can only split them up if they're convergent. We'll see this in practice, all right? For now, let's proceed. And we're going to start out with the integral test. So I would want us to take a look at a new series. Let's look at this series. Sum n equals 1 to infinity of 1 over n squared. All right, let's see how fast we can do this. Nth term test. Take the limit of that, goes to 0, fails, right? Okay. Is it geometric? Is the n up in an exponent? No. It's not geometric. Is it harmonic? That's not linear, okay? Is it telescopic? Well, can I split it up with partial fractions? No, I mean, it's just 1 over n squared, right? I can't factor n squared out to be, I don't have distinct linear factors, right? Yes?
Whenever you're looking to see if it's harmonic, are you always going to use partial fraction?
Wait, harmonic or telescopic?
Telescopic, I'm sorry.
Well, I showed you the one with the natural log just a second ago, right? That was not partial fractions, but it was telescopic, right? So I can't say you'll always use partial fractions. In this case, though, if I'm thinking telescopic, then I'm thinking partial fractions because you got a rational, basically a rational function, okay? So can we agree that I can't do any partial fraction decomposition on this? Do you all agree with that? So what's left? Right now, what's on our plate is nothing, right? We have nothing left. But we now introduce what's called the integral test. All right, so the integral test is actually, I think it's pretty simple when you think about it. What I'm going to do here is I'm going to plot this sequence, okay? This sequence. I'd like for us to plot that. So what would happen if I plug in 1? Plug in 1, I get 1 over 1, which is going to be 1, right? What happens when I plug in 2? 1/4. And when I plug in 3, 1/9, and this gets smaller, it starts to taper off, right? It starts heading to 0. That's what this sequence is doing. I should probably box this in blue to let you know that's what the sequence is doing. That's not what the sum is doing, that's what the sequence is doing. Now, when I say that I want to add those up, when I say I want to take Well, let's see. When I say I want to do this, that means I want to do 1 plus a 4th plus a 9th plus a 16th forever, right? Right? One way I could actually visualize that here is by creating some rectangles. So watch this. If I go up here and over here, how wide is this rectangle? 1. How tall is it? 1. So the area of that rectangle is 1, isn't it? Okay, if I go to this one here and go up and over, what's the area of that rectangle? Well, how wide is it? 1. How tall is it? 1/4. So the area of that is 1/4. Agreed? And then what about the next one? What's the area of this one? 1/9. And what's the area of the next one? 1/16. So I'm trying to figure out what all those add up to be, right? Now, I'd like us to consider the function of x, not the sequence, okay? The function of x, 1 over x squared, instead of 1 over n squared. If I asked you to graph that up here, and I don't have any other colors. Oh, I've got a green over here maybe. This green might work. If I were to ask you to graph this function, this is a function of real values of x. So that means it includes all the integers and everything in between. So this would be a nice smooth graph like this, wouldn't it? Wouldn't that? Like this? And do you agree that the area underneath the green is bigger than the area of the reds? Right? So what if I could show that the area of this was finite? That the area of this was a number? What would you be able to conclude? That this series must converge. Because this series is just adding up all these red areas, and the green area is more than that, right? And if that green area is finite, then so must that be finite, and therefore that must converge. Does that make sense? All right, but we have a lot of conditions that had to be met here for this to work. I had to pick a function. This function right here had to be a decreasing function, just like this right here had to go to 0, right? This has to go to 0. If this goes somewhere other than 0, then we know it diverges already. We know that, don't we? So if this goes to 0 means that that must go to 0, right? We also need that this thing is above the x-axis so that we make sure that our areas are always counted as being positive, because we know that when the area is below the x-axis, it's counted as negative. So we need this to be a decreasing function. We need the area to always be above the x-axis. And we need to actually be able to integrate that, right? Like I would have to show that this is finite. So we have a lot of conditions that need to be met. So let's bring up our sheet here, and let's take a look at this thing called the integral. See integral there? That's the integral test. It says that, let's say you have a series, okay? So you have an infinite series, and this is our a sub n right here. It says if you take this series and turn it into a function, now they say here function of n, but I'm going to say function of x. Is that all right? Then it says there are two things. It'll converge if the integral from 1 to infinity converges. So if I take the integral from 1 to infinity of this function, that's basically the area under this from 1 out, right? If that right here converges, which means if that goes to a number, then so does the series. Now, if this diverges, this is more complicated, but if this diverges, then this must also diverge. And that's actually really a nice result. Not as easy to see visually, but if this function starts to take off and become infinite area, then the series must do the same thing. Now, to the side, do you see on the right side with the comments, it says something over there? This is a comment, but it's very important. It says the function f obtained from the sequence a sub n must be continuous. which means that you can draw it without picking up your pencil. It must be positive, must be above the x-axis, must be decreasing, which means that it must be going down, and it must be integrable, which means you better be able to take the antiderivative of it. All of those conditions must be met to use this test, all right? Which means you have to show them before you start the test. You have to show it's continuous, that it's positive, that it's decreasing, and then you have to be able to take the integral. All right, so I'm going to do that now. You ready to do this problem? This was just kind of the setup for it. So I think, remember I said that I wish I could do chapter 8 first? I can't do a chapter 8 because to do chapter 8, we got to use an integral, right? If we didn't know what integrals were, then we wouldn't be able to do it. All right, so we look at this. Nth term test failed. It's not geometric. It's not harmonic. Telescopic. They're all out the window, right? So the only other hope I have now at this point is an integral test. So I'm going to let f of x be equal to 1 over x squared. Let's start talking about first thing on the list. I want to show that f is continuous. Now, how do I show that that function is continuous? Well, to do this, all I have to do is take a look at it and figure out any places that it's not defined. So where is that function undefined? Only at 0, right? Only at 0. And where am I going to be integrating from? 1 to infinity. Why are we going to be starting at 1? Because our series starts at 1, right? And so we don't need to look to the left of 1 at all. So I want to show f is continuous on the interval 1 to infinity, which it is. I'm just going to put a check mark next to it, since 0 is the only discontinuity. Since 0 is the only place where my function is undefined, right? So it's continuous everywhere else. So that's the first thing I've got to show. All right, what's the next thing I have to show? It's positive. I want to show f is positive on, on 1 infinity. Again, I only need to show that it's positive on 1 infinity because that's all I'm interested in integrating, right? I'm only interested in integrating from 1 to infinity. So let's take a look at our function. Is this obvious to you? Yes. Why is that obvious to you? Because obviously 1 is positive, right? So 1 over x squared, that's always positive. And when you square a number, it's always positive, right? So a ratio of two positive numbers is always positive. So we've got a continuous function that's positive, all right? Now what do I need to show? It's decreasing. Crap. How do I show you? Did I tell you about my office mate years ago that told me about that problem with his girlfriend? Yeah. Right? And he said the derivative of his love was always positive. Remember that? And the implication there was that it was always growing, right? Positive derivative would mean that it's always growing. So if I want to show that some function is always decreasing, what do I need to do? Show that its derivative is negative, right? That's how you can show a function's decreasing. Just show me that the derivative of it is always negative. Does that make sense? Okay, so I'm going to take the derivative of that function. What's the derivative of our function? Where's our function? Here it is. So don't forget, this is the same as x to the negative 2, isn't it? That's what that is. So if I take the derivative of that, that is negative 2, x to the negative 3, right? Which is the same as negative 2 over x cubed. Now, how do I know that that's always negative? Well, that number is always negative, right? And how do I know that that number is always positive? I'm only going from 1 to infinity, right? So, sorry, decreasing on 1 infinity, right? This could actually be a negative